In this segment, we'll talk about the prior knowledge needed for regression, and we will concentrate on finding the absolute minimum of a function. So in a regression model, in order to find what the constants of a regression model are, you will have to consider how to find the absolute minimum of a function. So let's go back to your differential calculus class where we talked about what an absolute minimum value means. So if you have a function f of x and it's in a domain D, then f of c, so this is c comma f of c, is the absolute minimum on this domain a comma g here, if and only if the function f of x is greater than the value of the function at c for all values of x in this particular domain here. So what we have to consider is that not only the points where you can see what the derivative is becoming 0, then you're also finding out that at this particular point the second derivative is less than 0. At this point the second derivative is less than 0, and at this point the derivative is greater than 0. And then also so those give you, hey, whether it's a local minimum or a local maximum. But you also have to look at the endpoints to be able to make sure that those are not below the minimum which you get from these critical points of where the derivative of the function is 0. So we will look at some of these things in the next slide. So let's go and look at the absolute minimum of functions which we use for regression. So when we will talk about regression models, we'll only find the absolute minimum of functions that are continuous and differentiable. So those are the kind of regression models we're looking at. So what that does is that it takes care of some of the things which we don't need to be concerned about now, is like functions which are discontinuous, functions which might be piecewise continuous, but they might not be differentiable at a particular point. So we don't have to be concerned about that. So if we are trying to find the absolute minimum of such functions, what we need to look at is that, hey, where is the derivative of the function equal to 0? So those are called the critical points. Now those critical points, when somebody says, hey, f prime is equal to 0 is a critical point, what that means is that either a local minimum occurs there, a local maximum occurs there, or maybe it's an inflection point, or maybe f prime of x does not exist. So we're looking only at critical points where f prime of x is 0. So we're not talking about places where f prime of x does not exist. And that's one of the things why we say, hey, we're only going to look at functions which are continuous and differentiable. So we are looking at critical points where the derivative of the function is 0. So there are three possibilities. One, it's a local minimum or a local maximum or an inflection point. Now, if we take the second derivative and it turns out the function is greater than 0, then we know that it is that these local extremes where we had these critical points, that it corresponds to local minimum. But that's not the only end. What we have to look at is that, hey, if we have several local minimums, then we have to look at the local minimums, and then we also have to look at the domain and function values. So all of these values, we might have a minimum, these local minimums at several points. Then we also have to look at the endpoints of the function. And out of all of those, we have to find the minimum of those values. Then out of those, whichever is the minimum is the absolute minimum value. And the value of the function at that point is then called the absolute minimum of the function itself. So there are two things which we have to be careful about, is that let's suppose we find the minimum is at xm. That is the point where the minimum occurs. Then we also have to think about another term, which is that, hey, what is the value of the function at that point where that minimum exists? So extremely important to understand the difference between the two and what we're looking for. Regression models will be only interested in where does this minimum exist, as opposed to what is the value of the function at the point where that minimum exists. So here we have an example where we want to find out the minimum of this particular polynomial. So this one is a continuous and a differentiable function on the domain, although it's not given to us, so we can say the domain is from minus infinity to plus infinity here. And then what we're going to do is we're going to take the make the first derivative test. So in order to do that, I have to take the first derivative of this function, which will be minus 20 plus 8x. And I'm going to see, hey, where is the first derivative 0? That means minus 20 plus 8x is equal to 0, implies x is equal to 2.5. So what this tells me is that x equal to 2.5 is a critical point, which means that either it's a local minimum or a local maximum, or it's an inflection point. So we don't know. So we got to figure out first, hey, is it an absolute minimum? So in order to do that, I'll take the second derivative of the function f, which will be the first derivative of the f prime value, which will be 8x. And f double prime at 2.5 is 8 times 2.5, which is 20, which is in fact strictly greater than 0. So what we can say is that x equal to 2.5 corresponds to a local minimum. So we have the derivative of the function at 2.5 to be 0. We have the second derivative of the function at 2.5 to be greater than 0. So the function has a local minimum at x equal to 2.5. Now, is this also a point of absolute minimum? So yes. Why? First, you are finding out that the value of the function, this function right here, when you look at the extreme points or the endpoints as such, is going to approach infinity at both of those values. So we don't have to worry about it being the absolute minimum. The second one is that we found out that there's only one point where the derivative of the function becomes 0, which is at 2.5. Hence, that tells us that, hey, this is going to be an absolute minimum at x equal to 2.5. So that's the end of this segment.